Hi everybody, I hope you guys are having a good day today. So in this lesson, we're going to be talking about numeration and some of the different methods that have been used throughout history to describe numbers or certain amounts of things. So to start off this lesson, I want to do a little activity. So I want you to pause this video, and in your notebook, I want you to draw a picture of a pig and draw a picture of the number 2. So pause this video, do this activity, and they don't have to be like super gorgeous pictures. You can just kind of sketch one out really quick. But pause the video and then restart it, and we'll have a discussion about this. Okay, so let's take a look at your first picture, and I want you to identify which one your picture looks more similar to. Does your picture look more like this? Or does your picture look more like this? If you're like 99% of my students that I've ever done this activity with, your picture very likely looks like this because I asked you to draw a picture of a pig. And a picture of a pig is not the same thing as writing the word pig. Now let's take a look at your second picture. So when you drew a picture of the number 2, did you draw it like this? Or did you draw something that looked like this? If you're like almost everyone that's ever taken my class, you probably drew it like this. However, this activity illustrates a difference between a number and a numeral. So the number 2 is the idea of having two things. And the numeral 2 is the name that we give that idea. Just like when I asked you to draw a picture of a pig, you actually drew a picture of the idea of a pig. But you didn't write the word that we use to represent a pig. And the reason that this is important is because when you're teaching little kids math, you want kids to understand the actual meaning of what a 2 is and not just memorizing the symbol. Because if kids are memorizing math from like the very first class that they ever take, it's going to make learning math really, really difficult for them because they're not going to understand the meaning of what the number actually represents. So a number is an idea or an abstraction that represents a quantity. So the number 3 is the idea of having 3 things. So if you were to draw a picture of the number 3, you might have like 3 stars or 3 dots or 3 people or 3 cows, but it's the idea of having a quantity of 3 things. Versus a numeral is the symbol or a combination of symbols that we use to represent a number. So this right here is a numeral. But the number 2,146 is the idea of having 2,146 things. And so this is a really key concept that we're going to be coming back to when we look at different ways to teach addition and subtraction and multiplication and division, because we want to teach kids those mathematical operations in a way that really communicates the idea behind it and not just memorizing a bunch of facts. Because what I've noticed as a high school teacher, because I taught high school for 7 years, is that the students who tend to struggle with high school math are the ones who started memorizing math earlier. But the students who tend to succeed in math are the ones who actually understand the idea that's being communicated behind, let's say, like the multiplication facts. So if you understand that 5 times 7 is 5 groups of 7 things, you're going to do much better in later math classes and also just in your current math class than if you just memorize, 5 times 7 equals 35. And you don't actually think about what that means. So this is the difference between numbers and numerals. And in our modern mathematical system, we have lots of different types of numbers. So when humans were first creating numbers, I guess you could say, or thinking about the idea of representing quantities, we started off with the counting numbers. So the counting numbers are like the numbers 1, 2, 3, 4, 5, etc. And it makes sense that these were invented first because the main or the easiest way to use numbers or apply it to real life is to count how many apples you have. Or if you were like a caveman, it might be valuable to know how many sheep you have in your flock so you don't lose any of them. So the counting numbers were invented first, and then we have the whole numbers. So the whole numbers include all of the counting numbers, and they also include the number 0. And it may not seem like a really big idea to include the number 0, but conceptually it's actually a pretty big step in logic to have a symbol represent nothing. Like they've done experiments, and one of the ways that they measure like the intelligence of animals is they measure whether or not animals can understand the idea of 0. So like monkeys and apes can understand using a symbol to represent nothing. And I think dolphins and I believe it was dogs can as well. But then there's some animals where like it just doesn't make sense to them. And I don't remember the whole way that they like set up the experiments to measure this. But basically the idea of having a symbol represent nothing is kind of like a added step of intelligence or a additional step of logic that a lot of even human civilizations, when they were creating their number system, they didn't have a symbol for 0 in many cases. So the whole numbers are all of the counting numbers with the number 0. And whenever you take the whole numbers, if you add any two whole numbers together, you'll get another whole number. So like if you choose, like 4 and 17. If you add 4 and 17 together, that's going to equal 21, which is another whole number. However, when you subtract whole numbers, sometimes you get whole numbers and sometimes you don't. Like if you do 7 minus 4, you get the whole number 3. But if you do 4 minus 7, that is not a whole number. And so the next level of numbers that were created were the integers, because the integers include all of the counting numbers, all of the whole numbers, and then it also includes the opposite of the counting numbers. So -1, -2, -3, etc. And the integers make it so that you can subtract any integer and you'll get another integer. Like if you do 4 minus 7, that gives you the integer -3, even though -3 isn't a whole number. And so that was the next layer of numbers that were created. And then the next layer after that was the rational numbers, because people noticed, well, if you multiply integers together, you'll get another integer. Like if you do -2 times -5, you get +10. But if you divide integers, they don't always equal another integer. Sometimes they do. Like if you do -10 divided by -2, that would give you +5. But if you did -2 divided by -5, that would give you a fraction. And so the rational numbers include all of the fractions. So, like 1/2 or 2/7, or basically any number that can be written as a fraction is a rational number. And then the next layer of numbers that were created after that were the irrational numbers, because people realized that if you are looking at maybe like the circumference of a circle, or the ratio of the circumference of a circle to its radius, that it actually can't be written as a fraction. It can be approximated by a fraction, but it can't be precisely written as a fraction. And so we came up with the irrational numbers, which include numbers like pi, or the square root of 2, or the number e, if you've heard about Euler's number. And those were the next type of numbers that came after that. And the combination of the irrational numbers and the rational numbers are called the real numbers. And so this is the type of numbers we work with the most. And there actually are more numbers than just this. Like if you square root a negative, that creates imaginary numbers. And then you also have numbers like the hyperreal numbers and complex numbers and things like that. But for this class, we're only going to focus on these sections, and we're going to spend most of our class looking at this region right here, because this is the region that you guys are going to be teaching to your students, because negative numbers and fractions and things like that don't come until the later grades. And we will also be talking about integers and fractions as well, because some of you guys will be teaching 4th and 5th grade, which is where those ideas start to be introduced. But we're going to start off by focusing on the whole numbers and the counting numbers. So when we're talking about whole numbers and counting numbers, one of the models that we use to think about this, which kind of goes back to our activity we did at the beginning where we were talking about the number 2 versus the numeral 2, is we look at the number of things in a set, because this can be described by whole numbers. And the notation we use for this looks like this. So if you see the notation n with a in parentheses, what this means is that is going to represent the number of elements in the finite set A. So for example, if I was looking at n of this set, that's saying the number of elements in this set, and then this is going to equal a whole number. So since there are 5 elements in this set, the number of elements in the set would equal 5. The number of elements in this set would equal 2. And remember that if an element is listed multiple times in a set, it's still just considered to be a single element in the set. And so the number of elements in this set equals 3, because this set could be simplified and written as 8, 6, and 1. Because those are the unique elements in the set, even though they were listed multiple times. So with this notation, we can define the words less than, greater than, and less than or equal to, or greater than or equal to. Because the way that we define these words is we say let A and B be sets, and let little a be the number of items in A, or the number of elements in the set A. And let little b be the number of elements in set B. So the way that we define the words less than and greater than is we say if set A is equivalent to a proper subset of B, then little a is less than B and little b is greater than A. So let's look at a set that might represent this. So let's say that big A equals the set, I don't know, let's say 7 to 5 or something like that. And then set B equals the set star, square, circle, triangle, or something like that. If we were looking at these sets, we want to look and see, is A equivalent to a proper subset of B? So is there a subset of B? So maybe I'll make a set C, so that A and C are equivalent to each other. So essentially, can I create a one-to-one correspondence from A to a subset of B? And I can, because I could define C to maybe be star, square, and circle. And there is a one-to-one correspondence from A to C. And C is a proper subset of B, because every element in C is also in B, and B has at least one element that is not in C. And so that means that it is a proper subset. And so what that means is little a, which is the number of elements in the set A, so I would say little a in this case is 3, and little b is 4, because there's 3 things in set A and 4 things in set B. Then that means that A is less than B and B is greater than A. So basically this is saying that 3 is less than 4 and 4 is greater than 3, which is true. And the definition for less than or equal to or greater than or equal to is very similar, except that instead of saying that's equivalent to a proper subset, it just has to be equivalent to a subset. So remember, it's possible for 2 equal sets to be subsets of each other. And so that's why we've got that or equal to piece. Because if you had the set, let's say that set A also had maybe like a 1 in there, well, then you would have to make your subset include the triangle so that you could have a one-to-one correspondence with that. But in that case, B and C are subsets of each other and they're equal to each other. And so that's how we define that. Now, obviously, when you're teaching this to students, you're not going to teach them the set theory definition of this because this is kind of like a complicated way of describing less than and greater than. And there's actually lots of different ways that you can teach this to little kids when you're ordering whole numbers. So one way that some people do it is they say, well, if you're counting and the number comes first, then that means that it's smaller. You know, so like if you're counting 1, 2, 3, 4, 5, 6, 7, because 2 came before 5, that means that 2 is less than 5. And you can also show this on a number line and you can say, well, 2 is farther down the number line than the 5 is, or like it's on the smaller side of the number line. And so that's another way you can show that 2 is less than 5. However, in my opinion, these are not the best ways to teach ordering whole numbers because they're both very memorization based. Like if you've ever listened to a little kid count, they'll often count incorrectly. Like they'll go 1, 2, 3, 7, 8, 9, and like they'll skip parts of the counting sequence. And that's because they're memorizing it. But if you can tie their understanding to the actual meaning of these symbols, so they're not just memorizing, oh, well, 2 is smaller than 5. If they can think about what those numbers, what those numerals actually mean, that's going to help them understand it more. So perhaps a better way to show that 2 is less than 5 is to make a pile of 5 things, which is essentially a set, and make a pile of 2 things, and you can show, well, the amount of things I have in this set is a littler or a smaller amount than the amount of things I have in this set. And this is a much more visual way of showing that 2 is less than 5 because it doesn't require the students to have memorized their counting sequence. It really just shows the concept of, well, this amount is a smaller amount than this is. And so that can be really helpful when you're teaching ordering of whole numbers. So the next thing we're going to talk about are some of the different numeration systems that have been used throughout history. Because what we currently use to represent the ideas of numbers is not the only way that humans have done it. Because if you think about it, like there's lots of different civilizations that have existed, and these different civilizations have come up with different methods for representing the ideas of different amounts. So the first thing we've got are tally marks. So tally marks, it makes sense that people would have used tally marks to represent amounts because there's basically just like a one-to-one correspondence where each tally mark represents one of whatever you're counting. You know, so if you were a caveman and you were counting your sheep, it would make sense that you could maybe have like a little board or something like that where you like scratch a line for each one of your sheep. And one of the key features that made tally marks more effective is when people started grouping them together, because this made it easier to interpret. So usually with tally marks, you group them together in groups of 5, which also kind of makes sense because we have 5 fingers on our hands. So it's kind of like, oh, like I'm going to count on my fingers and my thumb. And once my hand is full, then I'll start a new group of tally marks. So this numeration system is pretty simple, but it's also kind of clunky and ineffective for representing large numbers. Because if you have a very large amount of things that you want to represent, it's not very effective for doing that because you're going to have tons and tons and tons of tally marks. And because of this, people came up with different numeration systems that were more effective. For example, Egyptian numerals have different symbols that represent different amounts. So, for example, in the Egyptian numeration system, a line like this basically represents one thing. A loop like this represents 10 things. A curly rope like this represents 100, and basically all of these different symbols go up by powers of 10. And so when you look at an Egyptian hieroglyph, you basically just add together all of the numbers that are represented. So like this line and this line and this line and this line all represent ones. And so you could write this as 1 plus 1 plus 1 plus 1 plus 1. And then this symbol right here is the god, or like the exalted man symbol, which represents 1,000,000. So you would add 1,000,000 to that. And then these three symbols right here are these tadpoles. And so you would have 300,000s, like in our current numbering system. Sorry, I should have 3 of them. And then like these 3 symbols right here are the bent fingers, which represent 10,000. So you would add like 3 10,000s. These symbols right here are the flowers, or the lotuses, and they represent 1,000. So you would add those up. And then you've got 3 ropes, which would be 300s, and 3 loops, which would be 310s. And so the benefit of this is that by having different symbols to represent different amounts, it makes it much more efficient than trying to draw out, I don't know how much this would be. I think it's like 333,334 or something like that. Like if you imagine trying to draw out that many tally marks, obviously that's not going to be very effective. And so Egyptian numerals are much, much more efficient than, say, tally marks were. And so on your homework, what you guys are going to be doing is you're going to be converting Egyptian numerals to modern day numerals and vice versa. So let's go ahead and practice this. So pause this video, and I want you to take this Egyptian numeral and turn it into a modern day numeral. And then I also want you to take this modern day numeral and write it the way that Egyptians would write it. So pause this video and do that really quick, and then restart it to see what the correct answer is. Okay, so on this first one, the modern day numeral that would represent this Egyptian numeral would be 1,400,000. And then I don't have any bent fingers, so I wouldn't have any 10,000s, but I do have 2 lotuses. And so I would have 2,000s. And I have 3 ropes, which would represent 300s, and a loop, which represents 110, and 2 ones, which represents that. And so the correct number in our modern day numeral system for this Egyptian numeral would be 1,402,312. And then if you wanted to write this modern day numeral as an Egyptian, you would say, okay, well, if I have 3,000s, then if I look at my thousands, that's the little like flower symbol. So it'd look kind of like that. And I would need to have 3 of them. Sorry, my flowers are not super beautiful, but it's fine. So I have 3,000s, and then I would need to have 500s. So I would have 5 of these curly ropes. And then I would have 2 loops and 1 line. And so this would be the Egyptian numeral. Now, with Egyptian numerals, it actually doesn't matter which order you write them in. Because you could draw like my 3 flowers over on the right hand side of my numeral, and it would still be the same number, because Egyptian numerals, the placement of your numbers doesn't matter, because you just add them all up. And so I think from my understanding, I think the Egyptians usually tended to write them from largest to smallest, but you don't necessarily have to, if that makes sense. So that's how Egyptian numerals work. But the Romans came up with a different numeral system. So with Roman numerals, they had symbols that represented like ones. So they used an I to represent a 1, which is kind of like a tally mark. And then they used the symbol V to represent the number 5, X to represent the number 10. And then they said, well, if I have 10 5s, that's 50. So they had a new symbol to represent 50. And then they had another symbol to represent 100. And basically, they had the powers of 10, so like 10, 100, 1,000, and 10,000, as well as half of those. So like half of 10 is 5, half of 100 is 50, half of 1,000 is 500. But they had symbols all the way up to 1,000. And then after 1,000, they would use the same symbol but draw a line over it. So V with a line over it is the number 5 times 1,000. And so one of the unique things about Roman numerals that the Egyptian numerals did not have is the fact that Roman numerals are multiplicative, meaning that when they draw this line over their symbols, it means multiply this number by 1,000. So like CL is 150. And if you put a line over CL, that means you do 150 times 1,000, which would be 150,000. So Roman numerals were additive, just like the Egyptian numerals were, where like if you have C, L, XXXI, basically you say, well, C plus C, that's 100 plus 100. L is 50, so that's 250. Then I have 3 X's, so that's like 3 tens. So 250 plus 3 tens would be 280. And then you add 1, and that gives you the number 281. So this notation right here would represent the number 281 in our modern day system. And then it's also multiplicative. However, it's also subtractive. So with Roman numerals, if you have a smaller number before a bigger number, that means that you subtract it. So like IV equals 4 because V is 5, but the fact that there's an I right before it means that you subtract it. So IV is 5 minus 1. CD is going to be 500 minus 100, and that would equal 400. And basically this just makes it shorter because rather than having to draw out 4 ones, you can just write 2 symbols, or excuse me, not 4 ones, 4 I's. Instead of writing that, you can write just 2 symbols to represent the number 4. And so this makes Roman numerals positional because the order of the numbers matters. If you have IV, that equals 4, but if you have VI, that equals 6. And so the order matters with Roman numerals. And so when you're decoding a Roman numeral, you want to look at if there's any groups where you have a smaller number before a bigger number. So like XL, X is 10, L is 50. And so the fact that the 10 is before the 50 means that part of the number is going to represent 40. Versus like CM, that's 100 less than 1,000. And so that would be 900. Or I before V, that would be 4. And so when you're reading it, you want to read it from left to right and look for any numbers that are smaller than the number after them. And in that case, you would subtract them. So that's how Roman numerals work. And one of my favorite Disney movies is Hercules. And because it's a Roman story, they threw this little pun in here that I didn't get till I was an adult. But I thought it was kind of funny. Because this is the part where like Hades' little minions pretended to be little kids that were stuck under a rock to like try to draw Hercules out. And they were like, somebody call IXII. Which basically is like Roman numerals for 911, which I thought was kind of funny. So that's Roman numerals. And the next thing we're going to look at are Babylonian numerals. So the way that the Babylonians decided to upgrade from tally marks is with this number system. So the way that the Babylonians did it is they had 2 different symbols, and they did combinations of those symbols to represent numbers. So they had this symbol, which represents a 1, and they had this symbol, which represents a 10. And from what I understand, I think like their tools that they would use to create their numbers it was like they had like a stick, and like on one side of the stick they had the 1 symbol, and on the other side they had the 10 symbol, and they would stamp these sticks into like wet clay tablets and then let the tablets dry. And so that's why they only used 2 symbols, was because their writing utensil had like 2 parts to it. So they had a symbol for 1 and they had a symbol for 10, and then they would use this writing symbol kind of like a stamp. And the way that they would write their numbers is they would basically group these stamps together. So the number 28, for example, has 2 10 stamps and 8 1 stamps. Or the number 58 has 5 10 stamps and 8 1 stamps. But the thing that's interesting about the Babylonian numeral system is once they get up to 59, then they would start over. So kind of like in our number system, how when we count up to 10, we start over and we write it as 1 0. So like we don't have a unique symbol for 10. You know, like we have a unique symbol for 1 and 2 and 3 and 4 and 5 all the way up to 9. But once we get to 10, we reuse the symbol 1, but we put it in a new place value. So Babylonian numerals were a system that used place values. And so if you were a Babylonian and you saw this number, basically what this number has is 3 different parts. So you have this number, which is a 4. You have this number, which is a 23. And then you have this number, which is a 9. And this number right here is kind of like the 1's place value. So you would just have a 9. But this one represents 23 of counting up to 60. Because basically their number system would start over at 60. And so you basically have 23 60s. And then this number right here, or the 4, is telling that you've counted up to 60 60s 4 times. And so basically that's 60 squared, because if you have 60 groups of 60, then that's going to be 60 squared. And so this number here is basically a 4 in the 60 squared place value, because every time you count up to 60 in one of the place values, then you start over again. Just like when we count up to 10, like if you have 10 tens, then that's 100, or 10 hundreds is 1,000. So in Babylonian numerals, they would count up to 60 and then start over. And so if we were to convert Babylonian numerals into our modern day numerals, we would say, okay, well, we have 9 1s, we have 23 60s, and we have 4 groups of 60 60s, or 60 squared. And so we would calculate this out and we would say, well, 60 squared is 3,600. And if you do 4 times that, I don't know exactly what that is. That's kind of hard to do in my head. But you do 4 times that, plus whatever 23 times 60 is. And you would add that to 9. And if you add those numbers together, you get our modern day numeral of 15,789. And that's the way that Babylonian numerals work. So I want you guys to try interpreting these Babylonian numerals and converting them into modern day numerals, and then see if you can take this number and write it as a Babylonian numeral. So pause this video, try that out, and then restart it to see how I would solve it. Okay, so if I wanted to do this first one, I'm going to start with the smallest place value, and I'm going to figure out how many 1s I have. So it looks like I have the symbol for 10 4 times, which means that I have 40 1s. Then I would say, okay, well, now let's look at my next place value. Remember, this place value is basically going to be 60 1s, because once I count up to 60 in this red place value, then I would move on to my next place value. So the number of 60s that I have is 10, 20, 30, 40, and then it looks like I have 6 ones. So I have 46 60s. Because the 60 comes from the fact that if I have 60 ones, that becomes a 60 place value. And I have a 46 in the 60 place value. So I'm going to add these together. And then I also need to add this place value. So remember, this place value is going to be 60 groups of 60. So this is going to be kind of like the 60 squared place value, versus this was the 60 place value, and this one was the ones place value. Because 60 ones make 60, and 60 60s make 60 squared, or you could also calculate this as 3,600, because that's what 60 squared is. And so the number of 3,600s that I have is 10, 20, 30, 40, 50, and then it looks like I have 7 ones. So I have 57 3,600s. And then my last place value, this one is going to be 60 groups of 3,600. And so this one would be 60 cubed. And I just have one of them. So I don't know what 60 cubed is. That's not something I can do in my head. But I would have whatever 60 cubed is, and I would add that to 57 times 3,600 plus 46 times 60, and add that to 40. So I just went and calculated all of that out in my calculator. And you end up with these numbers when you multiply all of that. And when you add all of those numbers together, you get 200 and I think it's 32,000 if I added those right. And so that would be the modern day number that's represented by this Babylonian number. And then the second Babylonian number is a little bit easier because this part basically means that you have 27 ones, and then you have 2 groups of 60 because that's the second place value. And 2 times 60 is 180. And then if you add that to 27, that looks like that should equal the modern day number 207. And so that would be the Babylonian number for 207. So this last question is kind of interesting because on this one, we need to take our modern day number and convert it into Babylonian numerals. So the way we'd want to look at this is we want to say, okay, well, what's our biggest place value going to be in Babylonian numerals? So remember, Babylonian place values go by 60s. So I have a ones column, then 60 ones is 60, and 60 60s is 3,600, and 60 of those is going to be 60 cubed, which I calculated out equals 216,000. So if I want to represent the number 5,390, well, I'm going to have at least one number in my third place value because 5,390 has enough numbers to have a 1 in this column. So I'm going to maybe write this out over here. So I'm going to have 5,390, and I'm just going to subtract 3,600 to see what's left over when I have a 1 in that third column. So I'm going to actually kind of color code these so it makes it a little bit easier. So this one is going to be in my third place value, and I don't know how much is going to be my other 2 place values yet, but I know I'm going to have at least 1 in that third place value. And when I subtract those numbers, I think I get 90 and 17, I think. If you do 53 minus 36. And so I get 1,790, which means I don't have enough to put another 1 in that place value. So my third place value is just going to have a 1 in it. And so then the next place value I'm going to figure out is my 60s place value. So I basically want to say, okay, well, how many 60s are there in the number 1,790? So I might say, okay, well, I know that there's at least 10 60s because 10 60s is 600. So if I subtract 600, that gives me 1,190. I could subtract 600 from that again, and I'm going to actually draw these as I go. So here's my 10 60s that I subtracted once. If I subtract 600 again, 1,190. If I take away my 600 again for the second 10, that's going to be 590. And then I can't take away 10 more because 10 60s is 600 and I don't have enough for that. But I should be able to do 9, I think, because 9 60s would be 540. And so if I draw 9 of my little ones, this might take a little minute. But here's my 9 60s. Oops. Okay, so there's my 540. Then I have 50 left. And I can't put that in my 60s column because there's not enough to have 60. But I can have 5 10s in my ones column, essentially. And so my number would look something like this. And so this would be the Babylonian number for 5,390. And that's how you would do that one. So one of the things that's kind of interesting about Babylonian numerals is they would sometimes use a symbol for 0, but sometimes they wouldn't. So like, for example, if they had nothing in like, say, the 60s place value, sometimes they wouldn't write that. So like, it could be really confusing of like, oh, well, like, is this, 12 60s or is it 12 of the 3600s place value? And they recognized that this wasn't always very clear. And so they would sometimes use like a little separation mark to like separate the different place values if there was like nothing in one of the place values. But usually they wouldn't. And they would just kind of rely on the context of the situation to determine which like place values they were representing. So the Babylonians would sometimes use a symbol for 0, but sometimes they wouldn't. But the Mayans were consistent with always using a symbol for 0. And they would use this little mark here, which I think, if I remember right, was like a empty husk or something like that. And that's kind of what they used to represent 0. And in the Mayan system, they also had a place value system, but it was vertical because the Mayan language was written up and down instead of side to side. And so the way that the Mayan numeral system works is dots represent 1s and lines represent 5s, which I'm guessing probably was related to the fact that we have 5 fingers on our hands. So they would use like lines to represent 5s and then dots to represent 1s. And so in the Mayan numeral system, they basically would count up to 20 and then they would change place values. So the numbers 0 through 19 would be written like this. And then once they get up to 19, then they would move to a new place value and put a 1 in like the 20s spot and then like a 0 underneath that. So basically, it's kind of like with the Babylonians would count up to 60 and then they would start a new place value. The Mayans would count up to 20, which I don't know if this is the case or not, but if I was thinking about it, maybe like that's because we have 20 fingers and toes. So they would like count on their toes and their fingers. But for whatever reason, they counted up to 20. That was the number they would count to. So the way that you interpret a Mayan numeral is the bottom of the number is going to be your smallest place value and the top number will be your biggest place value. So this part right here is basically saying that you have 14 ones because you start with your ones place value and then your next place value. So if we look at this part right here, this is saying that we have 7 20s because the Mayan numeral system counts up to 20 and then it changes place values. And then the next one after that tells us that we have one of 20 20s, or 20 squared. And then the next place value above that, this part right here, tells us that we have 3 of 20 20 squareds, which is 20 cubed. So 20 squared, if I calculate out this part, maybe I'll do this right here. So if I have 20 20s, that's 400. And if I have 20 of those, that's going to be 8,000, I think. So we would have 3 8,000s. And then the next one tells me that I have 0 of my 20 to the 4th. Because if I have like 28,000s, that would be 160,000, I think. So I have 0 of those. And then the next place value above this, this one is a little bit misleading because like they didn't separate the lines super clearly. But like there is a little bit more space between this line and these 3 lines. And so what that one means is that I have 15 of my 20 to the 5th place value. And then my very last place value tells me that I have 5 of 20 to the 6th. And so basically the bottom of the number is the smallest place value, and then you just move up from there. And the reason that I know that this isn't like 20 is because their number system doesn't have a symbol for 20 because it changes place values. So like the way that the Mayans would write the number 20 would be with a dot and then with this 0 symbol. And that would be the Mayan number 20. So let's go ahead and practice this one. So I want you to convert these Mayan numerals into modern day numerals, and then also see if you can convert this modern day numeral into Mayan numerals. So go ahead and try that. Pause the video and then restart it to see how I would solve it. All right, so this first one right here tells me that I have 2 groups of 5, because like remember the lines represent 5s. And so that means that I have 10 1s in my 1s place value. And then this part right here tells me that I have 1 group of 20. And then this part tells me that I have 1 group of 20 20s, which is 20 squared. And then this part here tells me that I have 2 of 20 20 squareds, which is 20 to the 3rd. And so these place values, I'm going to actually calculate these out. I don't think I did this on the last slide. But basically this place value is the 1's place value. This one is the 20s. This one is the 400s because 20 20s is 400. And then 20 of those would be 8,000. And so when I'm calculating out what this number is, well, if I have 2 8,000s, that's going to be 16,000. If I have 1 400, that's just 400. If I have 1 20, that's just 20. And if I have 10 1s, that's 10. And so to find out what this numeral represents, I would add all of these together. And I'd say, okay, well, 16,000 plus 400 plus 20 plus 10 is going to be 16,430. And so this Mayan numeral is the same number as our modern day numeral of 16,430. And then the way that you would calculate the next one is very similar, because you would say, okay, well, this part right here tells me that I have 4 1s. This part right here tells me that I have 0 20s. And then this part right here tells me that I have 8 400s. And then this part of the numeral tells me that I have a 0 in my 8,000s place value. And then this last part right here tells me that I have 19 of my next place value. So I need to figure out what my next place value is. So if I think about having 20 copies of 8,000, well, 20 copies of 8,000 is going to be 160,000. And so I have 19 160,000s, which if I multiply 19 times 160,000, I get 3040 with 4 more zeros after that. So that would be 30,400,000. And then 8,000s is just going to be 0. 8 400s is going to be 3,200. 20s would be 0. And 4 1s would be 4. And if you add all of that up together, you're going to get 30,403,204. And so this numeral right here in the Mayan numeral system is equal to the same number as this modern day numeral. So they both represent the same amount. They're just two different ways of writing it because the Mayans use different numerals than we do. So if I want to write the number 4,280 in Mayan numerals, the way that I want to look at it is I want to say, okay, well, what is my largest place value going to be? So I have the place value 1, then 20 ones makes 20, 20 20s makes 400, 20 400s makes 8,000, and it looks like I won't have a fourth place value because 4,280 is smaller than 8,000. So I'm just going to have 3 place values, and I need to determine how much I need to put in each of those place values. So if I think of the number 4,280, I know that I have at least one 400 in it. In fact, I actually have a lot of 400s because if you think about, let's say, like 5 copies of 400, well, 5 copies of 400 is 2,000. So I'm going to subtract 2,000 away from this number and represent this in my numeral with a line, because remember, a line represents 5. So I'm going to put a 5 in my 400s place value. And when I do that and I subtract it, it looks like I still have enough that I could put another 5 in there as well. So I'm going to put another line in there in my 400s place value. And that's going to subtract another 2,000 from my amount. And I have 280 left over. And 280 is smaller than 400. So that's all I can do. I can just have those 2 lines in my biggest place value, which is my 400s place value. Then I'm going to say, okay, well, how much will I have in my 20 place value? So, and maybe I'll actually draw this in red so that the color coding is consistent. So this is representing the 400s place value. And those 2 groups of 5 400s are these 2,000s that I subtracted here. And then for my next place value, I need to say, okay, well, how many 20s do I have in the number 280? So 5 20s is going to be 100. So if I subtract 100, I can draw that as a line in my second place value. And that leaves 180. And I could also subtract another 100 from this, which leaves me with 80. And so that would be in my second place value. And then I can also say, well, there's more 20s in there because 80 is 4 20s. So if I draw 4 dots in that place value, that would take care of those 80. And what I'm left with is nothing else that I need to write to represent the number 4,280. And so that means that I'm going to have a 0 in my ones column. So I'll draw my little symbol for 0. And this would be the Mayan numeral that corresponds to the modern day numeral of 4,280. And we could check our work to make sure that I did this correctly. So we could say, okay, well, the red part of my numeral tells me that I have 10 in my 400s column. And the green part of my numeral tells me that I have 14 in my 20s column. And the blue part tells me that I have 0 in my ones place value. And when I multiply those together, 10 times 400 is 4,000. 14 times 20 is 280, and 0 times 1 is 0. And if you add all of those up, that does equal 4,280. And so that's how you would write the number 4,280 as that Mayan numeral. So that's how you do the Mayan numeral system. And on your homework, you guys are going to be converting between all of these different numeral systems. So my recommendation would be if you have, like if you're given an Egyptian numeral and you're asked to convert it into Babylonian numerals, you may want to first convert the Egyptian numeral to modern day numerals and then convert it into the Babylonian ones, because it may be kind of difficult to directly transfer it. But I hope you guys enjoy your assignment, and if you have any questions, let me know.